Well, looks like it's time. Welcome back, everyone. We're midway through week number 12. And what we have going on right now is we're pretty much midway through this unit. Well, more like we just started this unit, 8A, on linear growth versus exponential growth. Then when we take a look into unit 8B, this is all going to be about exponential growth versus exponential decay. When we work with doubling time, we're really going to be looking at exponential growth models. And when we look at half-life, we're going to be looking into exponential decay models. Well, the other announcement is our quiz 10 is going to be due tomorrow. And I'm a little bit behind on writing quiz number 11. I should have that posted sometime this after or tomorrow afternoon before we make it to class. I'm thinking the quiz number 12 is just going to be based off a couple problems in this unit here. But any questions or comments at all, folks, before we get started today? Okay, well, we also have for the further announcement that our third exam is going to be held on this week number 14. So we're going to be doing the same kind of pattern that we did before. I'll be posting the exam 3 information on Friday, and we'll be having our exam 3 review on Thursday of this week number 13. But let's get started. We left off on example 3 here. And these problems are all kind of random scenarios that we're looking into. We're just trying to determine if in these short contexts, is the growth that we're looking at going to be linear or is it going to be exponential? Linear growth means that the quantity is changing by the same amount in each unit of time, whether that unit of time is weekly, monthly, or yearly, the increase or decrease is always the same. If it's growing or decaying exponentially, that means it's changing by the same percentage in each unit of time. And I've noticed here in our author's definition, we're calling this exponential growth, but keep in mind, we're also thinking of growth allowing to be something that's negative when we say that definition there. Well, that takes us to example number 3. It says, after consuming a large amount of black coffee, the human body metabolizes the caffeine and removes it from the bloodstream. And the rate at which this is metabolized depends on the person, but if we're talking about the average person, then the metabolizing rate of caffeine will have the person's system decrease the amount of caffeine at a rate of 12% per hour. So based off this information, what would you all say for this one? Does this look like exponential growth or does this look like linear growth?
Exponential decrease.
Yeah, absolutely. And yeah, that word is kind of awkward, right? Because we drink coffee, our body is eliminating it. The amount of caffeine isn't growing. It's a negative growth. So probably better to call it exponential decrease. I like that wording. So the giveaway is it's not changing by, say, losing 50 milligrams per hour or something like that. It's decreasing by a percentage of the total every hour. So this right here is the giveaway that we're looking at exponential, and let's call that exponential. Decay specifically, because something is decreasing by a percentage. So exponential decay, since the amount changes by the same percent, in each unit of time. So now that we've looked into how the growth pattern is working on this one, really the decay pattern in this third example, we can do exactly what we did in example 2 and model how much caffeine will be at a given time. So we're assuming here a person has currently 800 milligrams of caffeine in their system, which is, by the way, is a lot. So this person's probably has the shakes or maybe they've just built a tolerance. So with a starting amount of 800 milligrams of caffeine, using this average right here, dropping 12% per hour, we'll determine how much is going to remain in this person's bloodstream after 5 hours. So the idea for this one is very similar with what we did in this problem. We were told that we had 30 milkweed plants, and that the number of these plants is growing at a rate of 18% per year. And since this was a true growth model, we wrote it out this way. Take the initial amount, 30 milkweed, multiply by 1 plus the percentage, 18%, and raise that to power 3, and it'll give us the amount in year 3. The only difference in our current problem is we can't use plus this time, we have to use minus. So we'll see exactly how this one goes. Hang on, let me Control Z whatever I did just there. Okay, I think that fixed it. Okay, let's use part B as a model. And let's suppose we're not going to jump to the very final line. If you wanted to, that'd be completely fine in homework and exams. If we went to the very last line, we'd just be taking 800 right here, 1 minus 0.12 for the 12%. It's asking after 5 hours, and this is changing at 12% per hour, so we would raise it to a power 5. So that's all we really have to do, but let's try to work our way to that end goal, just to show how it will work step by step. So at hour 0, the initial time, there is 800 milligrams initially. Hour 0 just saying here that no time has gone by. This is the moment at which we had that measurement somehow, some way. We know there's 800 milligrams. Maybe they just took a really strong, fast swig of cold coffee or something like that. Then hour 1 goes by. And we're going to assume that this, although it's an average, let's say it's exactly correct for the person in question, the amount of 800 has to decrease by 12%. So we could write that just using basic principles of taking 800 milligrams. It's decreasing, so this time we're subtracting. By that percentage means take 800 milligrams and multiply it by, well, not 12%. We want to multiply this, or hang on, yes, by 12%. Sorry, I got my numbers mixed up there. Multiply it by 0.12, which is the rate as a decimal. R equals 12% is 0.12. So this would get us started, and it's completely fine to compute like this. Again, what we want to put down on paper is an overall formula that just takes us right there, so it doesn't feel as much like busy work. But putting this into the calculator, we get 800 minus 800 times 0.12. So it'd be 704 milligrams after 1 hour goes by. It's decreased by just 12%. But you know, another weird way to do this is you could just take 800 times 1 minus 0.12. You get the same exact value if you wrote it out this way. And that's kind of more in line with how we were doing it on our prior problem, where it was exponential growth rather than decay. We just took 1 plus a percentage. The same idea here, we can either write 800 twice, but if you factor 800 out, you're left with 1 minus 0.12. Distributive law would multiply both here and both here, giving the original expression. And this is just a little bit faster to write. So we could rewrite this as 800 times 1 minus, because we're looking into a decay and something is decreasing, that percentage, but as a decimal, 0.12. And by the way, if you took 1 minus 0.12, that would just be 88%, the amount you're keeping, if it's decreasing by 12%. So either way we look at it, we are at 704. milligrams of caffeine. But that's hour one. We need to walk our way up to hour 5, kind of like how we were going down the years on this one. Any questions with this first row here? Okay, let's do it all over again. Now, 2 hours have gone by. Hour 2, what's decreasing by 12% per hour, but it's decreasing by the new amount on the each hour. So we need to take the 704 milligrams. If it's decreasing by 12% per hour, we can jump to this step right here, multiply it by 1 minus 0.12. And just redo that new computation below right here. So if we took that step, again, we're saving some time because we didn't write 704 twice. So that helps out a little bit. It would be 704 times 1 minus 0.12. So that's the new amount of caffeine in the system in milligrams. But you know, there's an even bigger shorthand to this. It's much like how we are writing out to year 3. Notice how we use the same initial amount on every single one of these years. We didn't actually have to get a value here, plug it into this one. And the reason is because we were bumping up the exponent. So if we worked a little bit differently and just started with 800 milligrams initially, took 1 minus 0.12, this is 1 hour going by. But if you want 2 hours going by, you raise that to just power 2. And you get the same exact figure either way you look at it. It's a little bit faster to write down in the sense that this informs us you could skip from really knowing the initial amount of 800 milligrams all the way to the 5-hour mark. You don't have to write down any of these computations. You can go right to the conclusion. But let's convey that shortcut on paper here. You can write out this way, walk to the final answer step by step, or you can just say simply that this is really 800 times 1 minus 0.12. On hour 2, we're at power 2. And that gives us the same exact figure, 619.52. No coincidence at all that these are identical. So 619 point, and I forgot the decimal, 52 milligrams. Then this is pretty much the pattern. We can put down the value for hour 3. It would just be this with a power 3 on it. Same for hour 4. But if we're getting this all the same values on every single one of these hours, at this stage, we can see exactly how to skip to the end answer. Again, we're pretty much just copying the idea that we took here. We want year 3. We take the initial amount, 30 milkweed plants, multiply it against 1 plus the growth rate, 0.18, raised to power 3. And likewise down here, if we want hour 5, let's put down a big conclusion. Therefore, hour 5, we take the initial amount, 800 milligrams, take 1 minus, because this is a decay model this time, put in the percentage, 0.12. And at hour 5, we just raise this to the 5th power. That's going to give us the answer in essentially one step. And I encourage you to use and abuse this last row right here. Same on the prior question. Just get right to the punchline. But if you prefer to see it in stage by stage, that's not a bad approach either. It's a little bit more writing, but you get to the same answer. So last thing we have to do, really could have been the first thing, take 800 times 1 minus the percentage, 0.12, raise it to power 5, and this is how much caffeine 5 hours later. 422 point, it says 1 decimal place for rounding, so 0.2 milligrams. And I'll box this out just to encourage everything above, was just discussing how this formula really goes. Let me highlight that negative one more time. But also keep in mind how context sensitive this was. In example 2, we were being told something was growing exponentially, so we had the plus. But in this example, we had to find that one key word that implies something is actually decreasing, going down. Thinking about the context, it makes sense. We don't become more caffeinated over time, unless we're being told we're drinking more coffee all along. And that's why we have the negative on this one. Well, any last questions or thoughts, folks, running through example 3? Okay, and one thing you might be feeling, like we mentioned before on Monday's class, is it's kind of deja vu when you do problems like these. We've essentially done something like this one, but it was in the context of money. So in this problem in Unit 4B, the power of compounding, we were talking about exponential growth, really in this section, or rather unit. We had a principal of 8,000. It was growing at a rate of 2.5%. So we wrote it as a decimal. We just want to know how much is going to be owed to this person after 6 years. So we did the same kind of steps as we did with our 1012. We did the step-by-step approach, showing how the values change by the percent, putting in the new values, change it by a new percentage. But then we showed we can just factor things out. And if we use exponential notation, we can use the initial amount, the original principal, much like we're doing down here with that 800 milligrams. The only difference between the formula in the box below and this one right here is the plus versus the minus. That's really the new thing in this unit. We're also looking at quantities decaying exponentially, not just growing. Well, we'll try out just a couple more examples. One more example using this definition right here that we screenshotted in. And then we'll be moving into the next unit. So here's our new kind of a random scenario. It says a household with multiple large dogs buys dog food in massive bulk orders, possibly wise, I'm not sure. The supply of dog food decreases by exactly 15 pounds per week as their dogs eat their daily meals. Well, this time it's exact. It's not increasing or increasing by any average amount, probably assuming that the dog owners are just measuring out their dog food, for example, using measuring cups or so on. And so they have a pretty good value that it's maybe not dead on exact, but pretty close to that amount, 15 pounds per week. I agree with Echo. This decay this time is going to be linear altogether. Again, our author only gives growth in his overall definitions, but something is decreasing, we would call this really linear decay. So it says decreases not by a percentage, but by an absolute amount, the same exact amount every single week. So we can say linear, and I like the word decay that you mentioned, linear decay, since the amount, which is referring to the supply of dog food, I guess we can just say that, the supply of dog food decreases by the same amount every week. I didn't use the word absolute amount in the definition. And really the reason the author used the word absolute is just to contrast it against relative, where we're thinking percentage versus a non-percentage. He's just trying to emphasize with the word absolute. So no percentage in the problem, dead giveaway. It's a linear change, this time decay, due to the decrease. Which means it's pretty much the same as our example one, doing our computation for if they had a fresh delivery of 180 pounds of dog food. I guess we're assuming that they were completely out before that fresh delivery occurred. So they have now exactly 180 pounds in their home. We want to know how much food will be left in 6 weeks. Again, that's kind of concerning. They ran out of dog food, so let's hope that doesn't happen again under this assumption. Maybe they were only out for exactly 1 day. Amazon Prime got it right on time. Who knows? But based off this problem, if they have exactly 180 pounds, that's the initial amount, like the 800 milligrams of caffeine. But finding a value after 5 hours for exponential growth is a totally different computation versus linear growth. Here, what we do this time is we take the initial amount, 180 pounds. We have to know that through the context, we're not using plus like we did on example 1. Something is decreasing, so we have to subtract from this total amount. But we expect that with the context. The dogs are eating the food, the total amount in the home is going down, and the consumption is going to be over a 6-week period, decreasing by that amount, 15 pounds per week. So we can take 15 pounds. Here's the per week unit. We're multiplying that against the value of how much is going to be left in 6 weeks. So we multiply by 6 weeks. Nothing too fancy happens with the unit. The weeks cancel. We have a value in just poundage. And so in the calculator for this one, take 180 minus 15 times 16, excuse me, 6 weeks. 16 would have been an emergency, right? We're in the red now. Times 6 weeks would get 90 pounds of dog food. So that's how much is left in a 6-week period. Hopefully the dog food isn't going stale at that point. Hopefully they have a good storage container for it. But any last questions, folks, on the linear case? Okay, well, lots of things change linearly. If you're thinking about, say, your daily commute to work, if you don't do anything too different on a weekly basis, your gas in your tank is decreasing by a linear amount. But plenty of things change exponentially. We're going to see lots of examples coming up in the next unit. And that's what this chapter's focus is really all about. Exponential change, growth versus decay. These are the main questions that we're going to see in the MyLab homework set. I have one more question on the notes that's kind of just a tie-in between this section and the very next one. Also a bit of a review problem at the same exact time. So that's going to be our example 5 down below. So the scenario on this one, even though completely made up, is slightly realistic in a certain scary sense. It says, suppose that a new payday loan company named Quicksand Financial just opened up in your town. So probably somewhere on the corner of Winco or something along those lines. Your friend takes a $300 payday loan, goes on vacation to Nepal. And they were told next, in ultra fine print, it stated that the APR on this payday loan is 12,000% compounded monthly. And that's pretty insane. It's a big exaggeration for what's even legally allowed in the USA. But in some states in our country, some of the worst payday loans actually have APRs in this range from 400% to as high as even 700%. So even though that's kind of a wild exaggeration, it's not that far off, which is, again, kind of scary in a certain sense. So 12,000% compounded monthly for this loan means effectively the balance on the loan will double every single month that goes by. So it's going to get kind of scary if you're thinking about the compound interest on this thing. This also means we're really just looking at exponential growth at the same time, changing by 12,000%. The time period is on every month. So this is exponential growth. So here's what we know so far. There's a principal amount borrowed, $300. We also know an APR, it's 1,200%. So the APR on this, recall we usually write this as a decimal, and it just looks funny because this is a humongous percentage. The decimal point is right here on the red dot. Go 2 place values to the left, and the APR as a decimal number is 12. 12, and that's it. We could put 12.0 to really emphasize we moved it over as a decimal, but either way, that's the APR as a decimal. It's compounded monthly, so that means the time period where it's going to increase, not by 1200%, but really by 100% is every month. So n equals 12 compoundings. Per year. So the next further part of the context says, suppose further your friend had a stunning transformative experience on their vacation to Nepal, and they just totally forgot about their payday loan for 2 entire years. We want to know, how much does your friend owe Quicksand Financial now that 2 years have gone by? So those 2 years are going to be the term of the loan. Realistically, for an actual payday loan company, it's probably going to go to collections really fast before even half a year very likely goes by. But again, this problem is a bit of an exaggeration to see what's going on in the next unit. So let's imagine this account is not in collections and they still want to collect even after term length of 2 years has gone by. The question is, how much does your friend then owe after the 2 years? So this problem really fits into the context of what we're working in. It's also a pretty decent review problem. After putting all this information together, essentially all we're going to do now is go down to, not this formula, this is annual compounding, but we just make a modification and divide right here by the red dot by 12. So let's put this down on paper. The amount owed is going to be the principal amount multiplied by a 1 plus and APR divided by 12 raised to the power of 12 times the term length. Actually, I was trying to write that down as a formula. Let me backtrack so we can see the formula, and then I'll plug in the values. APR divided by n to the power of n times y. Okay, so that's the formula. Now, if we plug in the given information, amount is going to be the $300. We're taking 1 plus APR, which is 12, dividing it by number of compoundings, 12 again, raised to the power of 12 times the term length, 2 years. So when we look at this, the format of this whole thing right here is entirely the same as what we did on example 2 with the milkweed. Only difference was the number of compounding had to be factored into this problem. And so that's why we have division by 12 here. So that's all the information plugged in. Now, if we simplify it just a little bit more, we have the amount is $300 times 1 plus 1 after simplifying inside the parentheses. 12 by 2 gives us 24 compoundings altogether. And again, if it's 1200 APR, that means the interest has gone up by a 1, but as a percentage, that's 100%, meaning it's doubling every single month. So this then becomes 300. The initial principal, simplifying inside here, it is now a 2. And that's where the doubling is coming up. This is over a term length of 2 years, which means it's doubling over the 24 months, 24 times in those 2 years. So if we take a principal amount of $300, double that 24 times, this amount grows astronomically fast. But we're expecting that because it's exponential growth. So here's the setup so far. Any questions at all, folks, before we dump it into a calculator? Okay, so here's the amount now owed after forgetting about the payday loan for just 2 years. So that's 300 times 2, Well, with that times 2, that's just after 1 month has gone by. But 24 months have gone by, and this is the value. It's in scientific notation, so this is amount in billions when we see power 9. It's grown really, really large. So let's put the value down, 5.0331. That's a lot of digits to memorize. 648 times 10 to the power 9. And it doesn't even look like it's fully accurate. It looks like they just gave us an answer that had 1, 2, 3, 4, 5, 6, 8 significant digits altogether. It had to essentially round at a certain point. It didn't show all the digits. So let's rewrite this in terms of just ordinary commas. The amount owed is going to be 5. Now we start moving the decimal place. 1, 2, 3 places. 4, 5, 6 places. 7, 8, 9. There's where the zeros come in, where it's been effectively rounded to the nearest 100th. And no cents. So the friend owes $5 billion to Quicksand Financial. They're probably not going to collect on that. But again, that's the power of compounding. And if we're looking into exponential growth where things are doubling in a short time frame, like monthly, $300 grows to $5 billion extremely rapidly. We're talking, say, in terms of maybe 5 years, we would take 12 times 5. But at this point, this is more money than the entire global economy at this point. This is 10 to the power of 20. Does even make sense once we go to 5 years. So exponential growth doesn't even make sense in the long term. There's no way anyone is going to pay that amount down. And the whole problem is even silly in the short run of 2 years. No one's going to collect on $5 billion, more likely than not. Well, any last questions at all, folks, on this final example here? Okay, well, with this information, we're going to go to our next main objectives. In Chapter 8, Unit 8A was more about just telling between different growth patterns. And Unit 8B, now we're going to really specialize into looking into both exponential growth and then exponential decay at the same time. So I want to just change this just a little bit. Drop it to about this line here, and let's open up the next unit's notes. Okay, now we suddenly have more formulas in this unit, not just definitions like we had before. This is broken up into doubling time. And when we think doubling time, here we're talking about exponential growth. Exponential growth in the sense of, say, the milkweed plants in the garden or the quicksand financial problem we were just looking at, both had exponential growth as a pattern. We'll also be looking into formulas for half-life. And when we think about half-life, here we're looking into exponential. Decay. Exponential decay just in the same sense as the problem where someone had 800 milligrams of caffeine and the amount decreased by 12% per hour. So those are our two different kinds of sides of these notes. For exponential growth and decay, there's going to be a couple pairs of formulas. One will be calculations with a doubling time to find a brand new value. And then the next formula that goes along with growth will be finding the formula for doubling time, an approximate formula, and then an exact formula. And then we'll do it all over again with exponential decay. This section is a little bit longer than the prior one, so we'll take our time with this and really kind of think of it as really just two halves that we're looking at simultaneously. Well, this starts it off. Let's take a look at our very first definition. It says, after a time t, an exponentially growing quantity with a doubling time, which we'll call T double, will have increased in size by a factor of 2 to the power T double. So T double is going to be one of our major things we're looking at. Actually, let me highlight this. And something increasing with that doubling time increases by a factor of 2 to the power T double. So once we know something is growing exponentially, if we have the doubling time, the time it takes for a value to double, this will tell us how much it increases by. And to find the new value relating to initial value at an initial time is 0, we just take the initial value, multiply it by that factor, time divided by T double, and that will give us our new value. So we have an initial value here, multiplied by the doubling time, and this gives us the new amount. And in fact, we've essentially used this formula, not exactly in a direct way, but in an indirect way. This is exactly what was going on. The initial value in our prior problem we were looking at was the $300. This had a doubling time of 1 month. So right over here, the factor is going to be 2 to the power of 24 months into 2 years, divide by the doubling time, but that was just 1 month. So that's really a 24 divided by 1 really altogether. And this was the factor that it increases by after the 2 years have gone by. We take that factor here, multiply by the initial amount, and it gave us the new value, the $5 billion, 33 million and some change owed to Quicksand Financial. So this calculation right here just comes out directly with the model that we computed using first principles all the way back from these formulas back in the day with compound interest. All we're really doing is looking into these kind of growth models a little bit more closely and in different kinds of contexts, not necessarily just money on every example. Well, that's a formula. That's how it kind of loops in with this example from just the last section. Any questions about the formula at the moment? Okay, again, if we're looking into doubling time, we're thinking about exponential growth. And that means something is going to increase in size by that factor. When we do the other equation, it's going to look very similar, but something is going to decrease in size by a new factor here, not 2, but rather just 1/2. And we'll call this not T double, but T half, or the half-life. So here's our new example. It says a culture of E. coli, so I'll just say this one, not sure how to pronounce the scientific name here. A culture of E. coli bacteria in a controlled laboratory setting is growing exponentially, and we're told it has a doubling time of 6 hours altogether. So these questions are kind of tricky in a certain sense. We're not always looking for a new value, depends on what the question is really asking us to do in MyLab. Sometimes the whole question is about the factor that it increases by, and that's it. Other times it's both the factor and the new value, so we have to be really critical when we read the questions to figure out which part are we even using in the formula here. So part A says, by what factor does the bacteria population increase in 48 hours? And in MyLab, I duplicated the notes here in the homework as well. They're really specific. They want exponential notation. That's pretty much what we were doing right here. The factor that the amount increased by to Quicksand Financial was just the 2 to power 24. So if we did this problem in 8B, that would have been the answer to part A. So all we have to do here is use the factor for doubling time. Before we use that factor, we should just state what the doubling time is. Let's see, we're told has a doubling time of 6 hours, so it's helpful to just write that down on paper. T double is 6 hours altogether. So now the factor that the E. coli bacteria is going to grow by is going to be 2 to the power of some time. The time is 48 hours. So that's the numerator part right here. When we see t to the power of t divided by t double, we'll go 48 divided by 6. So that's our whole formula. Once we compute this, this turns into 2 to the power. 6 goes into 48, 8 times. And so our answer is 2 to the power of 8 is going to be the factor that the total size of this E. coli bacteria will grow by. Oops, sorry, let me get back to there. Uh-oh, I think I closed the wrong document. Hang on, sorry, I'm having some issues with my Word document here. Oh no, it undid my highlighting. Let me fix this real quick, sorry. I tried to close the other document, but closed the wrong one. Probably shouldn't open too many of these at once. My highlighting went this. I'll rewrite those notes I had before that got erased for doubling time being exponential growth, half-life being exponential decay. Let me put a little note here or just some space to come back to it. I'll do that on my own time so you don't have to watch me retrace this whole set of notes. So this is going to be T double is 6 hours. The variable T here is 48 hours. And this is 2 to the power of 48 divided by 6, done a second time. So 2 to the power 8 altogether. I noticed my document was running slow, so I tried to close another one. Closed the wrong one on us. Well, any questions at all, folks, with the refresh notes to this stage? Okay, again, it's kind of a strange problem because we're just looking at the growth factor over a time period of 48 hours. If we happen to know that there was, say, 30 E. coli cells, we could take 2 to the power of 8 and conclude that after 48 hours, there's this many cells. But that's not what the question was all about. We just want to know the growth factor, 2 to the power of 8. And it's weirder still because it's tempting to say 256, and I'm happy with that answer on a quiz or an exam. But my lab is very specific. They really want exponential notation, so this is the only way you could format the answer. Well, that's how much it's going to grow by, the growth factor in 48 hours. And now part B is the same kind of question, but it's asking for 14 days. That means it's a trickier question in a certain sense. We have to do unit analysis on this one, returning back to our work in chapter 2, because if the doubling time is in hours, the variable t and t double must be in the same unit. So that's a unit conflict right away when it says 14 days. So let's make a quick note here, just as a word of warning. T and T double must have the same unit. It must be referring to the same amount of time, in other words. So first step we have to take here is take the time of 14 days, do a conversion. If the doubling time is in hours, we need to have something in hours. So we place days in the denominator for a conversion factor to cancel just right. And we can say, well, we know 24 hours is in 1 day. I'll just write HR for hours. This gives us a cancellation, and now we're just taking 14 times 24. So back to the calculator, 14 times 24 gives us 336 hours that have gone by. And with that set up, we can now use this equation. the growth factor the population increases by in 14 days is going to be 2 to the power of the time, 336 hours, divide by the doubling time of 6 hours, which now we can return back to the calculator again. We're getting some good calculator use in this unit. 336 divided by 6 gives us a power of 56 altogether. So 56 doublings of this size of the population of E. coli bacteria. So we can now say the population of E. coli increases by a factor of 2 to the power 56 in 14 days. So if we, again, had a larger question going on here, if it asked us, what's the population size after 14 days? Maybe they gave us an initial population size to work with that. If it started with 50 and we know a growth factor of 2 to the power 56, then that will tell us this many bacteria using scientific notation, 3.6 approximately times 10 to the power of 18, E. coli in 14 days. That may or may not be reasonable. That just depends. This is bacteria that's growing in a controlled laboratory setting. It's probably in a petri dish where there's a growth medium, but eventually space and nutrients run out, and it might not actually be growing at that rate any longer at 14 days. The exponential growth model is only valid over finite time intervals, not forever. So eventually, after you go enough days out, the model will break down. But if it's accurate on the 14-day mark, that's the growth factor. Any questions at all, folks, getting through this one? Okay, it's a weird question because once again, usually we want to compute something, a dollar amount or the actual number of bacteria after 14 days. But all we're doing here is using half of the formula. And I think I had other highlighting here that I missed. This was blue for initial value. Our problem just didn't have one. Echo says, do the doubling time and half-life calculations mostly have to do with calculating the life of bacteria? It kind of depends. There's going to be problems that have things like these, populations of things growing, say bacteria. The next one is a little bit, let's see, yeah, not about bacteria, but this is about a plant growing and invading a territory. But when we think about, say, decay, we're going to look into things like, hang on, this is still growth, the growth domestic product going up. This one is the consumer price index going up with an exponential growth model. Finally, we go to half-life where the decay models are coming up. And our examples for decay models are going to be medical tracers, like the one for this particular scan for Parkinson's, that has a half-life. So this is a substance that's injected into you. So imaging can be done on a region of your body, a brain in this case. This one has a half-life, 13.2 hours. This one is going to be about a population that's endangered, decreasing over time, and other random scenarios. This one is about deforestation, decrease in amount. This one's about a glacier called the Doomsday Glacier. That's a real glacier on the planet. So really back to the larger question about half-life and doubling time, the context could be pretty random. Doesn't always have to be populations like these. It seems like these are usually a common source of examples, but we'll see a pretty wild variety just in these notes as well. Same within the reading and the homework exercises. Other questions at the moment? Okay, again, I think example one is weird in my opinion because It was focusing just on this part, the growth factor, and nothing else. The next question goes a little bit differently because we're going to be computing a new value somewhere down the line as we look into this question. And so here's how the example 2 goes next. This is a brand new formula, so let's park it on paper just for the refresher on it. This says a cove within Toledo Bend Reservoir, so this is a real location in the United States, is newly infested with giant salvinia. I think that's pronounced giant salvinia. This is an aggressive, voracious, free-floating aquatic fern. And just to get kind of a feel for what's going on with this context, let's take a look at that. Usually when we say ferns, we think of things that are nice. And this is the fern. It has some nice close-ups. They don't look that awful as a plant, but this is kind of a nasty plant in the sense that when it really starts going, it blankets the water and completely kills everything below it. It completely darkens out the sun. So these are like blackout curtains. So these can be devastating if they're introduced into locations that they never belonged to in the first place as an invasive species, essentially. They grow very rapidly. It's a voracious species of plant. And we're told that initially, the invasive weed forms a dense mat covering an area. And I made a quick revision on this problem here. It was initially 1 meter, but that's going to be an initial value. And I felt like putting a 1 here kind of made that value disappear. So I changed it to 3 meters to make it actually show up when we write down the notes. So sorry for that quick revision right there. So we have an initial invasion of giant salvinia in this location in US, initially covers 3 square meters. It says next, during the early unconstrained stages of the invasion, the area covered doubles every 3.5 months. Assume that the fern is growing exponentially. It's kind of conveyed already that that's the case with that doubling time there. We'll round our values to the nearest whole number. And maybe before we even start going on this problem, there's 2 important values they gave us. We're told with a nice kind of keyword there where it said initially, the invasive weed covered 3 square meters in area. So kind of a different kind of problem really, right? This isn't number of bacteria. This isn't number of people in a population. The thing growing is the actual area that this plant is covering, not say the individual members of the species of this plant. So the initial area is, I'll write this as 3m squared for 3 meters squared. We're also told that there's a doubling time. It doubles every 3.5 months. So in our formula above, the way that's formatted is just T double is 3.5 months. Okay, so with that information there, really what this question is all about is calculating the new values. We want to know how much is the giant salvinia going to cover this reservoir after 3 years, and then again after 5 years. So that's the context breakdown, really just looking for the key words. Next, we'll drop it into the formula to find the area coverage. Any questions at the moment before we launch into the formula? Okay, really, once we have the two parts, the initial value, the doubling time, and a value t for time here, 3 years, and another time here, all we're doing is just dropping information right into that formula. Let's write, when it says 3 years, t equals 3 years. And so that means the new area is going to be equal to the initial area, which was 3 meters squared, multiply against, we're going to use 2 to the power of t, 3 years, divide by t double. Hang on, didn't see that problem right away. There's one additional problem with this, right? We have a unit mismatch, and I should have looked at my own little warning right there. T and t double must have the same units. So let's back off that right away. We can't take 3 divided by 3.5 because that's years divided by 3.5 months with a major unit mismatch. So we'll come back to this spot, fix the unit in our time right here. If it's 3 years, we can say multiply by the 12 months to the 1 year, and that gives us the correct time value. So this becomes 36 months altogether. Okay, with that correction, again, watch out for that misstep there. That's not a good mistake to make. It can make our values way, way off. We're taking 2 to the power of 36, divide by t double, which is 3.5 months. And this will give us the new area coverage for the invasion of the giant Salvinia. So all we now need to do is throw it into a calculator. And again, when you look at this, this is pretty much the same thing as the quicksand financial problem, where this was $300 and 2 to the power of 24. Slightly different values because the doubling time isn't the 1 month, it's 3.5 months instead, but almost the exact same kind of thing that we're looking at. So plugging this back into the calculator, take 3 times 2 to the power 36 divided by 3.5. And in terms of square meters to the nearest whole number, this would be 3,745 meters squared. So it started with just 3 square meters. And if we just ignore it in the reservoir, easy to do, it's a pretty big place. The entire area of Toledo Bend Reservoir is probably in the millions of square meters. But the invasion is going to start causing problems eventually. Ignoring it for 3 years means it's covering almost 4,000 square meters now. Any questions at all, folks, with part A? Okay, well, nothing too different in part B. We want the new surface area, this time after 5 years. This time we're ready for the unit conversion. We can't plug 5 divided by 3.5. It's got to be written in terms of months. So take t equals 5 years, multiply by the 12 months per the 1 year. That's going to give us 60 months altogether. And so now the new area coverage for this plant's invasion, it'll be equal to the initial area, 3 meters squared. Multiply that by 2 to the power of 60 months. It's going to double every 3.5 months. So this tells us how many times it doubles. That's just the growth factor. So 2 divided by 3.5 altogether. Let me fix my penmanship a bit there. So back to the calculator again. Write out in a similar way. This is 3 times 2 to the power of 60 divided by 3.5. And it's gone from just under 4,000 square meters to now, in 5 years, that's almost 500,000 square meters. It's just exploding in this reservoir at this point. But we should expect to. It's growing exponentially. So give it enough time to really get started, and we start seeing these wild amounts right here. So 434, 145. Meters squared. Let me check that was rounded accurately. Oh, we're off by a bit. 146. I usually don't worry too much about small rounding errors like that, but again, my lab will, so we have to be extra careful. So that's just after 5 years. Any questions at all, folks, getting that area of the coverage down? Okay, and we might wonder, what happens if it's not 12 times 5 for the 5 years value? That's the same numbers we have here. What if we let 10 years go by and just ignore the problem? Now it's at 10 to the power 10, and this coverage is probably bigger than the entire area of the Toledo Bend Reservoir. It's growing exponentially at first, maybe even from years 3 to years 5. But eventually something's got to give. By around year 10, it's out of area, it's out of space to expand to. The exponential model is going to fail eventually. But if there's enough potential area, if we're talking about maybe the Great Lakes or something like that, this exponential growth could go on year after year until it once again reaches the bottleneck. It'll run out of resources, space, food, and so on. Eventually, exponential growth model will fail. Well, that's our quick rundown with exponential growth. There's one thing that's really missing from all of these questions that we've done in example 1, example 2. The problem just told us right out of the gate a doubling time of every 3.5 months. So that begs the question at this point, what do we do if we don't have a doubling time? What if all we knew was the growth rate of the giant salvinia every month? Like maybe it's growing at a rate of, say, 27% per month. How can we get the doubling time thereafter? So that's what the next set of formulas are going to be all about, approximating doubling time. So as far as doubling time goes, first rule, it might sound familiar from finances, is going to be the rule of 70, and it's an approximation formula. We'll also give an exact formula for folks who are really curious of how to do this exactly, no approximations whatsoever. But our textbook focuses on the approximation formula for a good amount, and so do the exercises. So we'll do the same in the notes as well. So here's what the rule of 70 is trying to say. If a quantity is growing exponentially at a rate of p%, so now we don't know the doubling time, we just know the growth rate. Much like on our exponential models in examples from Unit 8A, like the caffeine and the milkweed, we had percentages. We didn't have doubling time whatsoever. But if we wanted to, you could go back to those units and find the doubling time in those particular examples. It's tricky because when it says p% here, we put p here, and we do not convert p to a decimal. Not the way our author wrote down this formula. And that's really, really weird, to be completely honest. On just about every time we did a computational formula using an APR, which was a percentage, we always took the percentage, wrote it in as a decimal. In fact, in the last unit, 8A, that's what we were doing with the percentages. But if we're using this rule of 70 to find the approximate doubling time, this is the rare exception where we don't convert back to a decimal. Again, it feels really weird. It kind of goes against our training for this entire semester. So we'll make a big deal out of that every time we use the rule of 70. And the bad thing about this rule is it breaks down for high growth rates. It can't be used in the quicksand financial problem, that APR of 1200% per year. It is only effective if your growth rate is not over 15%. So that's the boundary where it becomes a bad approximation. If it's smaller than 15% or right at 15%, it's decent for what we're doing in class. Well, any questions at all, folks, with the breakdown for the rule of 70? Okay, well, let's give it a try. Let's do just say the part A, so we're not rushing through this whole example. Part B is kind of the larger question that we're going to take a look into. using the prior formulas. But part A is just the rule of 70 that we've stated up here. So here's our new context. This time we're talking about the size of an economy. And a great way to measure an economy size, an okay way to measure it, it's controversial, is the gross domestic product, abbreviated as GDP. The GDP is the total monetary value of all finished goods and services produced within the borders of a country during a specific period. That's a really short definition. There's more into that definition, but that's a fast way to say it for our purposes. We're not taking an econ class, for example. It serves as a broad scorecard for the economic health of a nation. And we're told next, economists calculate GDP to measure the size and growth rate of an economy. So here's our next part of the context, just one sentence. The gross domestic product of the country of Panama is increasing at a consistent rate of 4% per year. So when we see the 4% per year, thinking about the formula here, we would be saying that P is 4. Again, we don't say 0.04 like we would have done if it was an APR, converting it into a decimal. We just say 4, no conversion, we drop the percent sign. It's all that's happening, going from the rate of increase to the rule of 70. Kind of strange in a certain sense. So part A, whenever these questions come up, will be specific. Use the approximate doubling time formula is referring to this one right here. If we're ever using the exact doubling time formula, instructions will indicate that as well, both on notes here, quizzes, exams, as well as on MyLab. So we want the approximate doubling time formula to determine the doubling time of Panama's GDP to the nearest tenth. So all we have to do is say that T double is, I'll write approximately to be honest, it's just a rough approximation. Take 70 divided by that rate without the percent symbol, so divide by 4. So back over here, this is 70 divided by 4, giving us a 17.5 years. So that's our doubling time. If the percentage is given per month, we would have said 17.5 months for doubling time instead of years. So whatever the unit is here for time, we match up down here for the doubling time as well. So if the GDP continues to increase at 4% per year for Panama, we expect their GDP value itself to double every 17.5 years, is what this approximation is telling us. Well, we'll return back to part B, looping in the formulas and refresh them when we come back on our Thursday's class. But any last questions or thoughts at all, folks, with the doubling time here? Okay, again, this section is kind of larger. Our book is a little bit unbalanced when it goes from unit to unit. Really, unit 8A was just kind of an introduction to the chapter. And this is a kind of a longer unit in the chapter. The next unit is a little bit smaller, but we'll be working these problems carefully, showing how each of the examples glow, possibly finishing this one when we return on Monday of next week. But have a great night, folks. We'll come back Thursday a little bit more fresh, review the formulas, and try out a couple more problems, and then turn to decay. Well, take care. Oh, good question. So for quiz number 10, let me take a look at that with you. I wrote it, but I already forgot what it was all about. Okay, so yeah, so for this one right here, for this particular graph, you can go back to unit 5D, graphs in the media. Actually, I think I have that pulled up right here. And take a look at example number 4. Example number 4 is going to be pretty similar to that particular quiz number 10. Yep, you bet. Thanks for asking about that.